Hey everyone, welcome back to another homework walkthrough video. We're going to jump right in. So this is question 5 of homework 4. And just to get started, we have a physician wants to characterize flow within the arterial stenosis illustrated. So that is right here. She knows that the upstream diameter D1 is 6 millimeters. The average blood velocity, assuming steady flow, so that's great, we have steady flow, is 40 centimeters per second, and the static pressure P1 is 100 millimeters of mercury. And we have the diameter at the stenosis, D2 is 2 millimeters, so that's D2. And the downstream diameter, D3, is 3, so that's here. So we have D1, D2, D3. Great. So the density of blood is also given. It's 1060 kilograms per meters cubed. So then we have the physician inserting a side hole infusion catheter and a mercury manometer, which is not in these three images at least. And we can measure pressures in the artery through this catheter. And we have the catheter diameter. So this is 3 FR and 1 FR is 1/3 millimeters. So just know the diameter is going to be then 1/3 millimeters times 3. Okay. Sorry, 1/3 millimeters. There we go. And then we have a central guide wire lumen, which is right here in the middle. Then we have the small side holes are located 3 millimeters distal from the guide wire opening at the end of the catheter, and that's just right over here. So that's not too relevant for this first part of the question, but let's keep going. Then we have the catheters inserted from the downstream end of the artery. So this is downstream, right? If we think of a stream going down, this is downstream, this is upstream. So we have it being inserted downstream end of the artery through the stenosis and well past point 1. And this is point 1 right here. So going all the way through as seen in this image, okay? Great. So let's get started. What is the stagnation pressure, PS? Well, we know first that the stagnation pressure, PS, so let's write that out, stagnation pressure, PS, is given by the pressure out when we have a simple condition here. When outlet velocity is 0. So that's where stagnant, right? Stagnant is not moving. Stagnation pressure is when the fluid goes down this all the way and then stops at velocity equals 0. That is the stagnation pressure, the pressure at this point when velocity is 0, right? So this is derived by a simplification from the conservation of energy. So we're going to start by deriving the general formula for stagnation pressure. So this is a simplification of conservation energy. Okay, so let's get started. We're going to write out Bernoulli's equation. So we're not going to write out the full conservation of energy because every time simplifying it from there just takes a long time. We know that in a streamline for an incompressible steady state flow that also doesn't have any friction, we know that we can use the simplification for Bernoulli's, right? For the conservation of energy. So it's given by the following statement, and this all should be reviewed for you at this point. So let's start out by writing this. And then let's begin the simplification. Okay, so here is our Bernoulli's equation. Let's get started by assuming that we're going to be traveling along a horizontal streamline. So Remember that the catheter is already inserted, so we're going to assume that we're going to take this streamline right along the catheter right here, that it's not going to be not through this area, right? We want to go through the stenosis right over here. So we're going to assume that we're going to be examining this streamline, meaning that, right, we have a horizontal streamline, so that means the H components will be equal, right, and therefore cancel each side, right? So we can, right, assuming horizontal streamline. Great. Then what's another simplification we can make? We know that blood, right, is incompressible, meaning that rho does not change throughout the system, okay? That is good, right? So that means that there is no rho in, rho out. It's just going to be rho. So I'm not canceling out this rho term here. I'm just canceling out the in and out sublabels. So let's write incompressible and remind us that rho is not changing, so it is a constant, okay? So these two things tell us that we can therefore make the simplification, and that brings us to having, we have pressure in over rho plus v in, velocity in, squared over 2, and then we canceled out that gravitational term, so we have equals p out over rho, and that is it? Not yet. So now let's make our final simplification. We know up here that we said outlet velocity is equal to 0. So that is what allows us to solve. So that is 0. That allows us to solve for the pressure out. Remember, we defined it as the pressure out when velocity is 0. So we need to now solve for pressure out. So that means P out is equal to, we have P in, right? Because the rows cancel out when you multiply this entire left side by rho, plus rho v in squared over 2. So this gives us our stagnation pressure. So P out is our stagnation pressure. So I'm just going to write PS is equal to P out. And when you solve for this, plug in your terms, you will get the pressure out. One more thing to keep in note is we are given units. We have pressure in as 100 millimeters mercury, right? Let's just write that out real quick. Pn equals 100 mmHg. And we have also rho given in terms of kilograms over meters cubed. And we have velocity in is equal to 40, it's right here somewhere. Where was it? 40, there we go, 40 centimeters per second, right? So instead of changing our units all at the very end, it's easy to make some unit changes here that we know allow it to cancel, right? For example, we know 1 millimeters of mercury is equal to around 133.32 pascals. And pascals is simply kilograms over meters times second squared. Okay, so now we can kind of get a general idea of what units we need to change in order to actually multiply these terms out. Okay, that's why writing out units is really important. Okay, so this is where that first challenge comes in. So let me just write the definition right here, is stagnation pressure. Okay, so you can use this definition on an exam. I just wanted to show you where this comes from. Okay, so let's keep going. That is part A of this question. Part B is asking us, use the conservation of mass and Bernoulli, right, which is energy, right? And it wants us to calculate the pressures P1C, P2C, P3C, and V1C, V2C, V3C, the velocities, with the catheter in place. Okay, now before we keep going, let's think about what happens when we put the catheter in place, right? You can see right here, the catheter, right, takes up cross-sectional area in flow. It's blocking flow. So we need to remember that we need to account for this catheter in the cross-sectional area of flow. So without it, we have flow right here in this whole section. But now with the catheter being blocking some portion of this flow, we need to remember it's going to block this area of the flow. So we need to calculate the area of this remaining part without the catheter, okay? And same goes for here at the stenosis. We have a block, right? So right over here. And same with at the end, right? We still have a block right here. So we need to really remember that we need to take the cross-sectional area of flow. So it's a slight challenge problem. So how do we go about calculating these cross-sectional areas? Well, first, let's write it out. A1 comma C, right? One catheter. So this is 0.1, this is 0.2, 0.1, 0.2, 0.3. I put a dot just to not make it look like pressures, but yeah, great. So let's keep going. So we have the simple area of a circle, pi r squared, right? And instead of r, we are given diameter, right? So if we have diameter, divide by 2, right? Inside the square. And we have to subtract the area of the stenosis. So that is the diameter of, or not the stenosis, sorry, the catheter, dc over 2 squared. So that's what you're going to do for the remaining two positions as well. So you need to find these, right? And one more note, right? The diameter of the catheter is defined by 3 FR, which is 3/1/3 millimeters diameter, right? So we need to really be critical when we read these questions, making sure we're getting all of the information given by the question, okay? Although that's probably 1 or 2 points off an exam, it is really important that we're writing down these key numbers and variables and we're understanding the direction we're trying to head to, okay? So let's continue on with this question we have. It's asking us for the conservation of mass, which is always the first part where we want to start, right? So that is great. We know our simple conservation of mass, dm dt is equal to m dot in, right? The mass flow in minus the mass flow out, mass rate, right? Plus m wall, plus or minus, right? We don't know the sign, but we also know that there is no leakage, did not state in the question. And we also know that there is no accumulation, right? That would be very bad for our arteries, right? If we have any accumulation. So we have it at steady state as well. So we have m in is equal to m out, right? But let's think for a second. It's not just m in, m out. Let's make it really specific to our problem. That means it's going to be m dot 1c, right? Catheter is equal to m dot 2c, right? Let me draw out what that is. So we have our 1 right here, and we have 2, right? 0.1, 0.2. So that means we at least modeled this first half. What about the second half? So we have it going slightly, but not the same size as the original. So we have 2, and then we have, and I want to just make it look a little bit better. Like that. So 3. So that means we can also model the same exact conservation of mass for also 0.2 to 0.3. And that means it's going to be, we're just going to go from this line right here, this line. So 0 is equal to m dot 2 catheter minus m dot 3 catheter. So that means we have m dot 2 catheter is equal to m dot 3 catheter. So that means we can combine all 3 of these statements, or all 2 of these statements, sorry. So we have m dot 1c is equal to m dot 2c And because we said over here, M2C is equal to 3C, so we can write M dot 3C. Great. And we know that this fluid, this blood, right, is incompressible, right? Because incompressible, right? Rho is a constant. Therefore, we can write it out as B1C times the area of 1C is equal to V2C times A2C is equal to V3C times A3C. Okay. So that is where we get this. Basically, what happened here is the rows cancel out on each expression, right? Because it is incompressible. Let's keep going forward. So what are we solving for here? Well, from earlier, we already determined the areas, A1C, A2C, A3C. So the question is asking for our velocities. So simply, we need to figure out the velocities. But we know velocity of 1 without the catheter is 40 centimeters per second, right? Not the velocity with the catheter. That is not what we were given. But let's think about it, right? If we extend this a little bit further back, right? So let's remember this is going to be somewhere over here is 0.2, but let's say this is 0.1 and we have the catheter. So let me first model the catheter. We have the catheter right here, and this is 0.1. Well, if we say this is 0.1, right? That means we also have the velocity here without the catheter going at 40 centimeters per second. So this is 0.1 and this is 0.1c, right? We know that we can model this in the exact same way with our conservation of mass. dm dt equals m in, right? M in is our 1, right? Our 1 over here, m in, m out. So let's keep going. This will make sense in a second. So m dot 1c plus m dot wall. Simplify the conservation, right? That gives us m1 is equal to m1c, m dot 1c. And we know this because rho is also a constant, incompressible. That's why we can then write it out in terms of the entire expression, V1 times A1 without the catheter. So notice here, without the catheter over here, right, is going to equal V1 with the catheter times A1C is equal to V2C, A2C is equal to V3C times A3C, right? Let me show you where that is. So that means this area, right, is going to be V1C times A1C. This makes sense. This makes sense because we know that because we are at equilibrium, right? We know that velocity is dependent on cross-sectional area, AC. So we know that when we say in our conservation of mass that dm dt is equal to 0 and is equal to m in, right, minus m out, we know that if we decrease our cross-sectional area here, right, we will have an increase in our velocity and vice versa, right? So just remember that we can apply this throughout our entire actual model, okay? So I just want to show that right here. So that means with this statement that we just derived right over here, this entire statement, we can now pull out the V1C and the V2C and the V3C, right? So let's write it out. That means V1C, so that's the velocity at 0.1 with the catheter, is going to equal, we're going to just use this right here, V1A1, V1C, A1C, is equal to V1 times A1 over what? A1C, right? And you can solve for that. Similarly, we're going to also say what is V2C and what is V3C. And again, you can relate it stepwise like this. You can relate it like this, right? But also you can relate these two together because of equality. That makes sense because of conservation of mass. I'm going to reiterate this point one more time. But remember, at least because of the equal signs, equality, we have, then we can also say V1A1 over A2C, right? And same with here, we can say V1A1 over A3C, okay? I just want to highlight that because of our conservation of mass. That's where this all connects. Okay, let's keep going. I'm going to add a new page. Then it asks us for the conservation of energy, right? So let's start with that. And then I'm going to write Bernoulli. Great, so once again, let's just write out Bernoulli. We have Pn, and you should be able to do this in your sleep, hopefully, maybe not, but Bn over 2 plus Ghn is equal to P out over rho out plus V out squared over 2 plus GH out. Okay, let's make the same assumption that we're traveling along that same streamline, right? Horizontal streamline. And then we also have an incompressible rho, so, or rho is constant, so we're going to write that. Then this simplifies, and this time we're not saying velocity out is 0, right? That was for stagnation pressure, so that's slightly different. So we're going to now Pn over rho plus Vn squared over 2 is equal to P out over rho plus V out squared over 2. So we now simplified it to this. What are we solving for again? We are solving for P out, right? P out. Why? Because we need to find P1C, P2C, and P3C, right? And we are given P1. We know P1 before the catheter is inserted, okay? So that's how we're going to get there. So that is our Pn, right? So let's keep simplifying this for our P out. So we can then move everything over to one side. So P out over rho minus P in over rho is equal to V in squared over 2 plus, sorry, not plus, that's a big eraser, minus V out squared over 2. Then that simplifies to 1 over rho, right? P out minus P in is equal to 1/2 V in squared minus V out squared. And we can move the rho over as well as the P in. So that will give us P out is equal to P, let's go in order. Rho over 2, V in squared minus V out squared plus P in, moving that over at the very end. So this expression allows us to calculate the outlet pressure when given the inlet pressure as well as V in and V out, right? Great, so let's make this more specific to our example. So let's write out P out is going to be, well, P1C, right? The one catheter is going to equal rho over 2 V in, and our in is 1, right? Without the catheter. Squared minus V out. Out is, again, one catheter. Squared plus P in, right? P1, right? So we just basically did this for an inlet to an outlet that is going to be 1, right, to 1 catheter, right? So what if we wrote this expression for 1 catheter to 2 catheter, right? So let's write 2 catheter here. Well, we could write this in with basically what I'm trying to say is you can say 2C and 1C, sorry, 1C, 2C, and then 1C and 2C, right? But you would have to put in new values here and it would just make things a lot more calculated or complicated. So what we can do is when we write out this conservation of energy, instead we know that these two equal to each other, right? So what we can do is just use these two to make the relationship. So that means when we write that out, it will look like this. P 2C is equal to rho over 2 V. And instead of using 1C, we're going to keep using 1. Same thing as we did earlier. Minus V, and the outlet is 2C squared, right? So don't forget the squareds, plus P 2C. Okay? And we can do the same thing for 3C, right? Because 2C is going to be an inlet for 3C, right? And these two cancel out. They're equal as well, right? They're equal. So we can use, again, these two as the relationship, okay? One more way to show this is by saying, well, in this, right, we said out, in, right here. In, out, right, is going, well, this is 1C, 1C. This is 2C, 2C, right? It's equal to P3C, right? Plus V3C over 2 squared, right? And then we're relating these two right here. Does that make sense? So ultimately, this is what conservation is that everything is all connected through equilibrium, okay? All right, now let's start with part C and part D. So we have the physician pulling back the catheter until the side holes of the drug infusion ports are located at point 1. And it connects the drug infusion port to one leg of a mercury manometer. Okay, and we're given the specific gravity, 13.5. And the guide wire lumen to the other leg. And we have both the blood infusion port and the guide wire lumen are flooded with blood. Then we have a height of a manometer, H1. And the question is asking, what is H1? So let's think about what is our manometer really saying here. So we have, it looks like in the image, we have one side is higher, the left side is higher than the right side. So let's draw this out right here. And great, we have our manometer. So we have some height, H1, okay? And we know that, well, it looks like this left side is connected to the drug port, right? Which is actually exposed to the system, right? So we know that we have some system-related pressure on the left side, okay? So the system, and I'm gonna draw it up a little bit more, okay? So on this side, we have something related to the system. So we're gonna write P1C. And then on this side, we have the catheter, right? Which is not the pressure of the catheter itself, but we have it infused with blood, right? So that means blood, and it has a zero velocity, which then we can use our P stagnation pressure, right? So we know our stagnation pressure, and we are not given this height here. What is this height? Well, here's the thing. Let's think about what we know about manometers, right? So we know that, for example, at this height right here, right, we know that the pressures are equal because we're going down and up in a continuous fluid with the same rho. So the minus rho GH, the plus rho GH, with the same rho and H will cancel out. So they'll be the same, right? We can use that same exact logic up here for this height that we do not know, right? Because we are going down some unknown length and some unknown exact same length with the same rho, right? This is blood. This is blood right here, right? And this is also blood, right? So therefore, we don't really need to examine this part of the manometer, only right up to H, right here, right up to this line, because we know, right, that whatever we go down, up, down here will be the exact same up here, okay? So that's not really important, right? So that means, right, we know that this is going to be stagnation pressure at this point right here, PS, right? Stagnation, right? Now we actually know how to solve this problem, right? So let's keep going. We're going to say this is P star, right? It doesn't matter, some arbitrary pressure, P star, right? So that means we know, well, P star, right, is going to equal PS, right? Plus, since we're going down, so there's more pressure, rho, and rho what? Rho blood, right? Rho blood, G, H1, right? And we know up here, right, this is going to be P1C, right? P1C. Because remember, as we said, we're going down and up, so that's why it's negated, okay? So we know that P1C, right, is equal to P star minus what? Rho, right? Minus rho, mercury, Hg, GH1, right? So setting it equal to, or not equal to each other, but moving this right into our expression, we can solve something for our rho, right? And H. So let's keep going. So that means we have P1C is equal to what? P, stagnation pressure, right? Plus rho, blood, GH1 minus rho, Hg, GH1. Okay. Now let's simplify. Okay, let's simplify this. We have, and we also know that PS is going to be a little bit, it's going to be larger than P1C. Why? Because we know that it's pushing down more, right, on this mercury. So it's not necessary, but I'm just going to rearrange it so it looks a little nicer, okay? So that means it's going to be rho Hg minus rho blood. I'm just pulling out the rows, right? Times, we're pulling out the GH, right? GH1 is equal to PS minus P1C. So what I did was I moved this to the other side because I know stagnation is going to be larger, okay? So that means we now have something that we can pull H1 out of. So H1 is going to equal P stagnation minus P1 catheter over rho Hg minus rho blood times G. That's it. So now we're divided by G. So now we can see that we have an expression that solves for H1, okay? Now, before you continue here, just keep in mind that we are given our rows in different variables or different units, right? So we have rho Hg is given in terms of gravity, right? In terms of specific gravity. Specific gravity. Sorry. Oh my gosh. Gravity 13.5. Specific gravity is basically the rho of something over the rho of water is specific gravity, okay? So in this case, rho Hg, right, is equal to 13.5, right? And it's a ratio, so no units. And we know that rho H2O, right, is going to be 1 gram per mil, right? That's the density. So therefore, we also know, right, mil units can be converted to centimeters cubed, can be converted to 10 to the negative 6 meters cubed, right? So we do want to make these conversions prior to starting because it will make life easier when we cancel out units, make sure everything is good, okay? So just really keep that in mind. Now, finally, for part D, it's asking, what are the heights H2, H3, and H4, right? Well, let's think. Just imagine, what will our actual pressures be, right? So in this exact same way, you can use this expression that you derived for H2 and H3. So try to derive these, okay? Derive and then plug in and solve. So if you have any questions, please come to office hours, and I'm always happy to help. You can always email me too. And thanks for watching. Have a great day.